It's time to start. We'll do a little bit more in section 10.3, and then the remaining time we'll review sections 10.1 and 10.2, as well as 10.3. Okay, so last time we were getting a graph of this polar curve, r equals 2 times cosine of 3 theta. So one technique is to first graph r equals 2 times cosine of 3 theta in the Cartesian plane, where theta is the independent variable and r is the dependent variable, and then use this graph to get a graph of the polar curve. So I'll attempt to do that. So these subintervals up here are of length pi over 6. So I'm going to put dashed lines where the theta equals pi over 6 multiples. So approximately, this is pi over 6, and then opposite of that is 7 pi over 6. Then 2 times pi over 6, or pi over 3, the 60-degree angle will look something like this. And then in the second quadrant, 2 pi over 3. And then in the opposite direction in the fourth quadrant, and then this one. These are not exactly accurate, but so this one is theta equals pi over 6. This one is theta equals pi over 3, and so on. Okay, so from the Cartesian graph of r theta, when theta equals 0, the r value is 2. So when theta is 0, r is 2. So this is a point on the graph. And then between 0 and pi over 6, the r values are positive, and then 0 at pi over 6. So the r values are positive, they get shorter and shorter. And then at pi over 6, the r value is 0. So we get something that looks sort of like that. Between pi over 6 and pi over 3, the r values are negative. So up here, between pi over 6 and pi over 3, since the r values are negative, they have to be on the opposite side of the origin. So those will go, the r values will go from 0 to negative 2 between theta equals pi over 6 and pi over 3. So it's going to be over here, and it's going to be 2 units along that dashed line. Okay, so this is what gets us through pi over 3. The next interval is from pi over 3 to pi over 2. So up here, that's from theta equals pi over 3 to pi over 2. But the r values are negative on that interval. So on the polar curve, the graph has to be in the opposite opposite side of the origin from this interval. So they start out at -2, and then they go to 0. When we're at pi over 2. So here's pi over 2, and we're at 0. Okay, now what? Well, the next interval is from pi over 2 to 2 pi over 3. So that's between the y-axis and this dashed line. The r values are, from pi over 2 to 2 pi over 3, the r values are positive. So they will be in this, the graph will be in this section. And so it's going to end up, this r value is +2 when theta is 2 pi over 3. Is this making sense? Okay, then the next interval from 2 pi over 3 to 5 pi over 6, that's this interval, or this part of the plane. The r values are positive, so the graph will be in this region. They start out at 2, but then they get shorter, and then at 5 pi over 6, they're 0 again. So the graph will do something like this, and we're at 0. The next interval, 5 pi over 6 to pi, that's this region. But since the r values are negative, the graph will be on the opposite side of the origin in this region. So we start out at 0, and then the r values go to -2. So when theta is pi radians, the r value is -2, which means on the graph it's on the opposite side of the origin, and we end up at this point again. Okay, so I'll just do one more just to show you what's going to happen in this case. On the interval from pi to 7 pi over 6, that's this region in the plane, but the r values are negative. And so the graph will be on the opposite side of the origin from this part. So what we're going to get is just a retrace of what we've already graphed. So if we went all the way to 2 pi, we would just find that we would retrace this, this graph. Okay, a little bit later, if we don't run out of time, I'll explain how you know if you have something like this. This one's 2 times cosine of 3 theta. If you had something like r equals 2 times sine of 3 theta, it would also have 3 loops. They would occur in different places, of course, since it would be 2 times sine of 3 theta. But whenever you have something of the form, I'll just write it r equals a times cosine of some positive integer n theta, or r equals a times sine of n theta. Then whether the integer n is odd or even will determine how many loops there are. And a little bit later, we'll, if we don't run out of time first, I'll explain that in a little more detail. But for now, let's move on to the next page. Also from section 3 from chapter 10, we have a way to find equations of tangent lines to polar curves. So if we're given a polar curve r equals f of theta, we're thinking of theta as a parameter, then the parametric equations of the curve are x equals r times cosine of theta, but since r is f of theta, we can write that as x equals f of theta times cosine of theta. And also, since y equals r times sine of theta, we can also express y as f of theta times sine of theta. So just like we did with the parametric equations, we can use the chain rule to show that the derivative of y with respect to x is the derivative of y with respect to theta in the numerator, and then divided by the derivative of x with respect to theta. We did the same sort of thing when the parameter was t instead of theta a couple of days ago. Okay, since y equals r times sine of theta, or f of theta times sine of theta, well, we can just find dy d theta by using the product rule. Since both r and sine of theta are functions of theta, we have to use the product rule when finding the derivative. So dy d theta is dr d theta times sine of theta plus r times cosine of theta. And since x equals r cosine theta, or f of theta times cosine of theta, dx d theta is, by the product rule, dr d theta times cosine of theta minus r times sine of theta. So when we put that all together, dy dx is dy d theta divided by dx d theta, which is this numerator divided by this denominator that we observed in the previous step. So it looks sort of tedious, but it's pretty basic. So for this curve, find the points on the curve r equals 1 plus cosine of theta, where the tangent line is horizontal or vertical. So when will that occur? Just in general, so if dy dx is dy d theta divided by dx d theta, horizontal tangent lines will occur when? I shouldn't be using all my space to write this, but I can pull out some extra paper if I have to. So if dy dx is equal to dy d theta divided by dx d theta, horizontal tangent lines occur where dy d theta equals 0. So a horizontal line in the xy plane has a slope of 0, or when the derivative is equal to 0. So this derivative is equal to 0 when the numerator is 0. So we'll have a horizontal tangent line. How do you know that when you have a vertical tangent line? Yeah, when the denominator is 0, remember the slope of a vertical line is undefined. And so our derivative is undefined when the denominator is 0. So I'll throw that in. Vertical tangent lines occur where the denominator dx d theta equals 0. Okay, so we have this polar curve, r equals 1 plus cosine of theta. We'll compute dy dx, and then we'll find the theta values that make the numerator of the denominator 0 and the theta values that make the denominator of the derivative 0. Okay, so for r equals 1 plus cosine of theta, the derivative of r with respect to theta is negative sine of theta. Okay, so in our derivative formula up here, I can move this up and keep that in view for a while. Okay, so our derivative of y with respect to x. So we want the derivative of r with respect to theta, which we found to be negative sine of theta, multiplied by sine of theta, and then plus r times cosine of theta, but r is 1 plus cosine of theta. So this is the quantity 1 plus cosine of theta times cosine of theta. And in the denominator, the derivative of r with respect to theta is negative sine theta times cosine of theta. And then minus r times sine of theta, but r is 1 plus cosine theta. We multiply that by sine of theta. Then we do a little bit of algebra and arithmetic. So negative sine of theta times sine of theta is negative sine of theta squared. And then plus cosine of theta plus cosine of theta squared in the numerator. In the denominator, negative sine of theta times cosine of theta minus sine of theta minus cosine of theta times sine of theta. I'll just write it as minus sine of theta times cosine of theta. Okay, a little bit more manipulation. So notice up here in this numerator, two of the terms involve cosine of theta. So if I replace sine of theta squared with 1 minus cosine of theta squared, right, we'll use a Pythagorean identity. Since sine of theta squared plus cosine of theta squared equals 1, sine of theta squared is 1 minus cosine of theta squared. So I'm going to replace sine of theta squared with 1 minus cosine of theta squared. And since we're subtracting, it'll be minus 1 plus cosine of theta squared. So minus 1 plus cosine of theta squared plus cosine of theta plus cosine of theta squared. In the denominator, we have like terms that can be combined. We have minus 2 times sine of theta cosine of theta minus sine of theta. In the numerator, 2 of the terms are cosine of theta squared, so we get 2 times cosine of theta squared plus cosine of theta minus 1. In the denominator, let's factor negative sine of theta out of both terms. So negative sine of theta times 2 times cosine of theta plus 1. Okay, we're almost where we want it to be. The numerator can be factored pretty nicely. This is quadratic in form. So one of the factors is, let's see, 2 times cosine of theta. So I want this to be -1 and +1. Okay, let's find the theta values where we have a horizontal tangent line. So when the numerator is 0, so when 2 times cosine of theta minus 1 is 0, that's cosine of theta equals 1/2. So cosine of theta equals 1/2, or theta equals pi over 3. And that's not the only place. Cosine is also positive in the fourth quadrant. So that would be 5 pi over 3, right? So cosine of theta equals 1/2. That makes this numerator 0 when theta is pi over 3 and 5 pi over 3. The other factor, cosine of theta plus 1, that's 0 when cosine of theta is -1, or when theta is pi. Okay, then those are the theta values where we have horizontal tangent lines. I guess I can write that in, horizontal tangent lines. And then what about vertical tangent lines? When the denominator is 0, so negative sine of theta is 0, or sine of theta is 0 when theta is 0. And other places also, we'll come back to that later perhaps. The other factor, 2 times cosine of theta plus 1, that's equal to 0 when cosine of theta is -1/2. And cosine of theta is equal to -1/2 in the third and fourth quadrants. So when theta is 2 pi over 3 and 4 pi over 3. Okay, so we should have vertical tangent lines at those values. Well, you might remember from last time, I attempted to graph this polar curve, r equals 1 plus cosine of theta. So I'll put that drawing, for what it's worth, up here. So we were saying that we have horizontal tangent lines at theta equals pi over 3, which is about right here. So it looks pretty reasonable that we have a horizontal tangent line there at pi over 3, and also 5 pi over 3, which would be about right there. So we have another horizontal tangent line at 5 pi over 3, or negative pi over 3. This one also says at pi, and that's believable if this curve comes in and is, when it reaches that origin, if the tangent line is horizontal, that seems reasonable that it could occur there. Okay, so those are the horizontal tangent lines. The vertical tangent lines. Well, at theta equals 2 pi over 3, so 2 pi over 3 is right in here. So that looks like we have a reasonable argument for a vertical tangent line, both at 2 pi over 3 and 4 pi over 3. Okay, let's move on then to a review of 10.1 parametric curves. So let's sketch the curve, the parametric curve, by eliminating the parameter. So we have x equals t over t plus 2, and y equals the square root of t. Let's just note a couple of things. First, since y equals the square root of t, the t values must be non-negative or greater than or equal to 0. If we're going to remain in the realm of real numbers, then t has to be greater than or equal to 0. And what can we say about the values of x? If t must be greater than or equal to 0, then what are the possible values for x? I guess we can also say, since t is greater than or equal to 0, then y has to be greater than or equal to 0. And what can we say about x values? X will have to be greater than or equal to 0, and how much? Less than 1. Yeah. See how x is defined? If the numerator is always smaller than the denominator, then x can never reach 1. So x can be 0, but it has to always be less than 1. So we'll keep that in mind when we sketch the graph of the curve. Let's solve x for t. Solve this equation for t. I mean, solve that equation for t. So if we multiply both sides by t plus 2, we get x times the binomial t plus 2 equals t. Then xt plus 2x equals t. So we're solving for t. So we'll subtract xt from both sides. So 2x equals t minus xt. Then factor t out, we get 2x equals t times 1 minus x. And 2x divided by 1 minus x equals t. So in the other equation, we replace t with 2x over 1 minus x, and we get y equals the square root of 2x over 1 minus x. Okay, so to sketch the graph, we can only pick x values between 0 and 1, including 0 but excluding 1. We should come to the same conclusion just by analyzing this function itself. Okay, so we'll pick a few x values when x is 0, y is 0. And we're going to have a vertical asymptote at x equals 1. And this is sort of awkward, picking fractions and then evaluating them. Let's just do 1 or 2. So suppose x is 1/4. So we have the square root of 2 times 1/4, 1/2 in the numerator, 3/4 in the denominator. So 1/2 divided by 3/4. So we get the square root of 2/3. So 2/3 is 0.66 and repeating, so the square root of that would be about 0.81, something like that. So it looks like it's going to climb pretty fast, which we expect because when x values get close to 1, the denominator is small, so the number gets large fast, even though we're paring it down by taking the square root of it. So this is roughly what it looks like, but we know that it's going to be asymptotic to x equals 1. So that's a rough sketch. Hey, another thing that you should know how to do is parameterize a line that passes through 2 points. So we'll use the parameter t. So maybe you've already learned how to do this. I think this comes up in trigonometry, or it can if it's covered anyway. So in general, I'll just write down what you can do to parameterize a straight line. I'll just say a line that passes through points x sub 0, y sub 0, and x sub 1 and y sub 1. We just define x to be, let's see, 1 minus t times x sub 0 plus t times x sub 1, and define y to be 1 minus t times y sub 0 plus t times y sub 1. Let's use these points. So another way to do it, which is pretty informal. So if we begin with the points 2, 1, and 5, 5, if we multiply, like I say, this is a bit unconventional, but multiply each of the terms in the ordered pair 2, 1 with 1 minus t, add that to this ordered pair multiplied by t, and those will define x and y. So why will this work? Note that 1 minus t and t are both linear. And in this arrangement, when t equals 1, let me change that. When t equals 0, we'll start when t equals 0. We're at the ordered pair 2, 1. And when t equals 1, well, this factor is 0, and then we're at the other point, 5, 5. And we're assuming that t can be any real number, but for the t values between 0 and 1, we'll get from one point to the other. So it just depends on what you need. If you want a straight line segment between the ordered pairs, then we would limit the t values to be from 0 to 1. But if we want the full line, then t would have to be all real numbers. Okay, so if we make this a little more conventional, if we multiply 2 times 1 minus t, we get 2 minus 2t for the x-coordinate, 1 minus t for the y-coordinate. And then in the other one, 5t for the x-coordinate and 5t for the y-coordinate. If you want to write the equations separately, then x is 2 minus 2t plus 5t, which is 2 plus 3t. And the y-coordinate is 1 minus t plus 5t, or 1 plus 4t. If you want the full line, then t is any real number. Okay, let's look at some section 10.2 material for practice. Well, we did one of these already today, a little bit different than this one. Find an equation of the tangent to the curve x equals 2t to the third plus 1 and y equals t plus 1 quantity squared, corresponding to t equals 1. If we want to find an equation of a tangent line through a point, we have to find the point. So we want to find the x and y coordinates of the point when t equals 1. So I'll just write this as x evaluated at 1. So 2 times 1 to the third plus 1 is 3. and the function y evaluated when t equals 1, 2 to the second is 4. So the point that the tangent line passes through is the ordered pair of 3, 4. And then we need to find the slope of the tangent line. So we need the derivative. So remember how to find the derivative of y with respect to x if both x and y are parametric equations. So the numerator is the derivative of y with respect to t. The denominator is the derivative of x with respect to t. This will give us the derivative function. The derivative of y equals t plus 1 quantity squared is just 2 times t plus 1. And in the denominator, the derivative of x equals 2t to the third plus 1 with respect to t is 6t to the second. And then we evaluate this when t equals 1. So 2 times the quantity 1 plus 1, 2 times 2 is 4, and divided by 6 times 1 squared is 6. So the slope of the tangent line is 2/3. So the tangent line that passes through the point 3, 4, and with slope 2/3, we'll just write down the point slope form. Y minus 4 equals 2/3 times the binomial x minus 3. Okay, we already have the derivative of y with respect to x. So the horizontal tangent line when does that occur? When the numerator of the derivative is 0. So the horizontal tangent line occurs when 2 times t plus 1 is 0, or when t equals -1. And we can find the point in x and y coordinates when t equals -1. 2 times -1 to the third plus 1 is -1 for x, and then -1 plus 1 squared is 0. So the horizontal tangent line will occur at this point in the xy plane, and the vertical tangent line when the denominator of the derivative is 0. So 6t to the second is 0 when t is 0. And the ordered pair of the point when t is 0 is 1 for x and 1 for y. So even though we don't know really, I mean, we could guess what the graph of that looks like, but it's sort of hard to visualize because of the powers involved. Okay, let's try this problem. Find the area enclosed by the x-axis in the curve x equals the square root of t and y equals t to the second minus 2t. Okay, so here's the formula for area. If y is a function of x above the x-axis, then the area is the definite integral from a to b of f of x dx. But if this same function is parameterized by functions x and y as functions of t, then this can be transformed to the definite integral from alpha to beta of g of t times lowercase f prime of t dt. So this is where y equals g of t and x equals lowercase f of t. And the connection between capital F of x and g of t is that each one of those is equal to y. Okay, so we need to find the derivative of x with respect to t, because that's what f prime of t is. So this is just 1 over 2 times the square root of t. Oh yeah, what else do we need to know? How do we find the limits of integration for the transformed integral? If the area is enclosed by the x-axis in the curve, then we want to find the t values that make y 0. Okay, so y equals t to the second minus 2t in factored form, t times t minus 2. That's equal to 0 when t is 0 and t equals 2. So the enclosed area, if it's enclosed by the x-axis in the curve, it will have to be between t equals 0 and t equals 2. Okay, so our integral then from 0 to 2, g of t is what y is equal to. That's the t to the second minus 2t times f prime of t, which is 1 over 2 times the square root of t dt. We'll take it a little bit further. So we have this factor of 1/2. I'll just put it here, 1/2. When we multiply t to the second times 1 over the square root of t, that will simplify it at t to the 3/2. And then minus 2t over the square root of t, that's minus 2 times t to the 1/2. So you can do the rest of that. This is pretty simple to evaluate. For the next pair, I'll just write down the formulas for arc length for this problem. So for y equals a function capital F of x, the arc length from A to B is the square root of 1 plus capital F prime of x squared dx. But if that same function, capital F of x, is parameterized by x and y, then this becomes the definite integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. So since both x and y are given, just find the derivative of each of those with respect to t, square them and add them together and put them inside the square root. And then the limits will be from t equals 1/2 to 1. So we're out of time. I suppose on Monday we'll finish what we were talking about in this review, and then after that we'll start section 10.4. But that is all for today.